Yeah, thank you very much for inviting me to be here. Thanks also especially to Adam for hosting my visit here and being a great host. All right, so I'll be talking about pinning down privacy in statistical databases. So the talk is indeed about data privacy, and that means many, many different things. But we're at this point where all those meanings are changing quickly. Basically because data and data-driven systems are automating and guiding decisions in lots of areas of our lives that they weren't before. Everything from predictive policing to medical diagnoses. And the models that guide these decisions and in some cases make them are increasingly complex and hard to scrutinize. And so we're faced with this balancing act, where on one hand, we're trying to get the benefits of all this data we're collecting, and that could mean better policy, it could mean better science, it can mean better, a more efficient economy. But we're also trying to make sure we have tools to handle the potential negative impacts of these changes. And that can involve questions having to do with privacy. It involves questions tied to transparency and control and fairness and, broadly issues of power and who has it. So I'll be talking about one aspect of this balancing act, and specifically about statistical data privacy. So it's good to consider an example. Imagine you're dealing with an agency like the census. They collect information from a bunch of individuals, and then they have a mandate to make that information as available as possible for statistical analysis, but they also have a sort of a dual mandate that goes with that to provide a confidentiality guarantee to the people whose information they're collecting and managing. And the kinds of information they want to be able to provide, they range up from everything from like very simple summaries to complex statistical models, or the kinds of models that have been developed in machine learning of the recent years, to sort of synthetic data sets that somehow mimic or mirror the features of the real data as faithfully as possible. And this problem is not unique to the census. It comes up in all sorts of places where large collections of personal information are ubiquitous at this point. Census data is the classic example, but think of medical or public health data, data from social networks. Facebook, for example, is trying to make the data it collects available for policy development of various kinds, but that's delicate. Educational data is another great example. And in all these areas, you've got these sort of two basic conflicting goals, right? So on one hand, you're trying to provide, make the information as useful as possible. On the other hand, you are trying to provide some sort of meaningful privacy and confidentiality to the people whose data you're collecting. And that especially goes as, a lot of the data sets, the kinds of data we're now collecting, they're valuable, and having them available for analysis is sort of beneficial to society in various very basic ways. But what makes them valuable is precisely the fact that they paint such a detailed picture of our lives, right? And so that tension is really inherent. So a lot of what I'll be talking about today is what we mean by these terms. And so I'm not going to talk too much about utility. What we mean by the data being useful will vary from context to context, but by and large, it's well understood. The real question we'll be tussling with is what do we mean by privacy in these types of contexts? Okay. This is a question that's not new. It's been studied since the 1960s in statistics, in various fields of computer science. But I'll be talking about an effort that's gone on over the last 10 to 15 years to lay rigorous foundations for this area, rigorous mathematical foundations, that allow, and develop tools that allow us to reason precisely about it. Now, you might ask whether whether it's too late for privacy, right? We regularly hear, statements that privacy is dead. I don't think it is. We're generating new data all the time, and new kinds of data, new and more valuable data, even more sensitive data. Questions of data privacy are tied to very basic questions about freedom of speech, freedom of thought, freedom of association. And you just sort of have to imagine what it looks like to live in a society with no privacy at all to get like a sense of what that feels like. So this is a cartoon I like. I especially like the caption. Okay. All right. So this talk, what I wanted to do was talk a bit about why this problem is challenging, why privacy in statistical contexts is challenging, and I'll explain why maybe some of the straightforward approaches one would want to use don't work, and give you some examples of how that plays out. I'll talk about this notion that Adam mentioned at the beginning, differential privacy, which is sort of one formalization of this type of question. And roughly speaking, we're going to kind of try to define privacy in this context as a certain notion of stability to changes in the data sets, and I'll explain that when I get there. And this is a notion that at this point has been fairly widely studied, and it's led to a number of deployed systems. It's used as the basis, the kind of guiding principle for a number of deployed systems. And then, with what time I have left, I'll give you some snapshots of things going on in research right now in this area, and just some highlights of things I think are interesting. And then I'll talk more about a specific result of mine tomorrow in the math colloquium. Okay, so why is privacy challenging? So imagine, we've got a data set, and we want to make it available for use. The first thing, the thing we'd naturally want to do is to just remove the things that are obviously identifying, things like addresses or phone numbers or social security numbers, or, and just publish what's left. Okay. This is problematic. Sometimes the thing we want to analyze has to do with exactly where people live, for example. If you're studying an epidemiological question, you might need to know exactly where people are. But also, the real problem with it is it just doesn't work. So consider the following photograph, from which I've helpfully removed the face. Most of us recognize the person in the photograph fairly quickly, perhaps with a pang of nostalgia. And so what's going on is that, even though the face itself is blurred, you can see hair color and things like that. But there's this there are all these other cues in the image that we use, and that our brains tell us there aren't so many people who stand behind that, especially in color photographs, behind that podium, and we narrow it down pretty fast. Okay, so it's a bit of a toy example, but it's definitely a toy example, but it gets at really what's hard about this problem is that there's all this other stuff out there, all this other information about the world that you can use to infer things, and that make it hard to even distinguish what is identifying from what is not. That basically kind of tell you that distinction isn't really meaningful. And there's lots of research on giving examples of how this how this works, but this specific one is sort of funny because there's a paper on showing that if you take standard techniques for blurring people's images and videos, if you train image recognition algorithms on blurred pictures of faces, then they will actually recognize blurred faces pretty well, like the people in the blurred, the people whose faces are blurred pretty well. There's a great example in the context of biology where what you're looking at are genomic. This is genomic data, so you're taking people's genomes there's no name or ethnicity or anything attached to it, but you can sort of reconstruct lots of things about a person based on their genome, and in particular, you can for many men you can get a very good guess at their last name. Okay, and that's because most men in Western society inherit their last name and their Y chromosome from the same person. And so you get these long chains, and you can tie that. If you've got even partial data, partial public data sets, then you can use those to put names on genomic records. There was this nice study done of like a sort of supposedly anonymized data set of taxi rides in New York, where people sort of re-identified the riders and their destinations. I have some older work on what happens when you're using sort of things that were state of the art at the time. What happens when you have multiple data sets about overlapping populations. So imagine two hospitals that serve the same area, where you can find people in the overlap very efficiently, even though the data sets have supposedly been anonymized. And basically, these are just a few examples. There are lots more, but the lessons from these examples are that this sort of notion of what's an identifier is not really a meaningful concept. Everything's an identifier. And so we need a way to kind of think about this problem that doesn't kind of exclusively attach itself to that concept. Now, you might be tempted to think that the problem in these examples is the granularity at which information is shown. So in all the examples I gave you, that we're talking about trying to reveal a data set where sort of individual records are present in the thing I'm revealing, just in some limited form. Okay? And so, if we're only to release aggregate information, whatever that means, maybe we'd be fine. And the problem is that this concept of aggregate is itself like not so easy to pin down. And if you've got many aggregate statistics taken together, they can still encode the data in various ways. And sort of a trivial example is, imagine I tell you the average salary at a particular company immediately before and after somebody resigns. Right? So if you know how many people worked at the company, and you know those two averages, even though each of them on their own doesn't really tell you much, it's very easy to figure out the salary of the person who resigned at the time they resigned. Right? More generally, if we've got, there's sort of like a broad principle that's emerged over the last decade or two, which is that if you have too accurate statistics about a given data set, they will eventually, taken jointly, reveal very individual level information. And this comes up in what are called, in a couple of sort of threads of work in the literature, one on what are called reconstruction attacks, which I won't talk about so much more, but I'll mention this sort of a recent work showing how these reconstruction attacks, which were sort of sometimes dismissed as theoretical, were used recently to. There was some company that had anonymization software that put out a challenge saying, issued a challenge to try and break their technique, and it turned out the answer was in this sort of 2003 paper. You just had to read the paper and apply it directly, and it just worked. Membership attacks are another example that I'll explain on the next slide. But the kind of thing that we learn from all these examples is that there's a sense in which we can't release everything everyone would want to know about a data set. If the data set is sufficiently rich, then there's no way to release something that's useful for all possible purposes. And so we have to pick and choose. And there's a trade-off that actually needs to be managed, and we need kind of solid tools to do that. Okay, so I'll talk a little bit about membership attacks. This first came out in a paper by some biologists, Niels Homer and co-authors, where essentially what they looked at a data set of, in this case it was genomic data. They're showing how exact high-dimensional summaries can allow an attacker to basically test membership in the data set. Okay? So what does that mean? They could basically, if I know partial information about you, I could figure out whether or not your record was in the data set with some statistical confidence based on these sort of summaries. And this was the context for the biologists. The context was genome-wide association studies, where you're looking at, roughly speaking, the frequencies of which letters of the DNA are present at large subset of positions on the genome, and you're basically, for each of those subsets, you're telling me like how many, roughly speaking, how many of each kind of symbol are present in that string. So this problem, as exhibited by Homer et al., caused the National Institutes of Health to change their policy on sharing this type of information, on making it available. In another work that I was involved in, we sort of took that idea, and there were sort of several follow-ups on that Homer et al. Paper. We took that idea and showed that it could be adapted to deal with even fairly noisy statistics to which distortion had intentionally been introduced. And I'll explain a little bit what I meant by that. And then there's a nice paper by Reza Shokri and his co-authors showing some similar type of problem in the context of machine learning, and I'll explain a little bit about that too. Okay, so just to explain what I mean, suppose we have a data set in which membership itself is sensitive. So imagine you've got participants in a clinical trial. In the original context of Homer et al., they were looking at, there's a clinical trial, and the statistics are released separately for the cases and controls in the trial, and so I can figure out basically if someone who was involved in the trial was actually a case or a control. You can imagine this actually comes up also in the context of using what are called audience statistics in targeted advertising. So where, say you run a campaign on Facebook, you get to see statistics about the people who are looking at and viewing and clicking on your ads. What can you figure out about them, given that those statistics are broken down by groups? So you get separate statistics for different subgroups. And so membership here is like, in which subgroup does a particular person land? Are they self-identified as gay? I mean, whatever that statistic is, whatever that subgroup is. Okay. And so, so here's the model you should have in mind. We have some population that we don't necessarily know completely. From that population, some data set is drawn, and as a simple way to think about it, the data set is that it's a bunch of rows. Each row is a person, and each row has a bunch of attributes, and for simplicity, we'll just think of the attributes as binary, so zeros and ones. And think of the data as having many binary, many of these attributes, possibly many more attributes than there are people, at least at the level of granularity at which these things are released. So here, n, the number of people, you should think of it as like the size of the subgroup for which statistics are released. Okay, so for example, in the context of genome-wide association studies, you might have, anywhere from the thousands to millions of what are called SNPs, single nucleotide polymorphism. So these are just positions on the DNA, and a typical study size would not be that big. So here now what we've got the same setup. We're going to imagine that we learn the average of each of these columns. So just the frequency of ones and zeros in each of the columns of this data set. And now these frequencies are visible to some person on the outside. And that person also has some subset of Alice's data. So D here is the number of attributes about Alice that the attacker knows. And now that what the attacker's job is to figure out whether or not Alice was in the data set or out, meaning she's either in the data set or just a random member of the population, same population. And what Homer et al. Showed is if X bar is indeed consists of the exact column averages, then the attacker can succeed, at least with high probability, when there are, roughly speaking, more attributes than people. Okay, there's also a statistical assumption built in here that the attributes are not too closely, that they're not like all the same, that they're somehow independent. Okay, so that's the, sorry, let me, I lost my slide. Okay, so that's the kind of, that's a simple kind of statement. Homer et al., by the way, sort of historical note, were interested both in the kind of sort of implications about privacy. They were also interested in forensics because they were looking at, well, what happens if I've got, a blood sample where multiple people are in there. The blood of more than one person is in there. How do I get a statistically significant read on whether or not a particular person's blood is in the sample. Okay, so what we looked at were noisy versions of this question. What happens if you've got noise that's intentionally introduced? And we considered the following simple model where in each component of the released information, what is released is within some error tolerance. We'll call it alpha. It's just some bound on how far away the released quantity is from the true quantity. But we don't want to assume anything beyond that. We don't want to assume whether or not the kind of error distortion that was introduced was somehow coordinated across columns or anything like that. Okay? It doesn't have to be independent. But now we imagine that, so what the attacker sees are these distorted statistics, and what we showed is basically the similar result. The attacker succeeds with high probability as long as there are A, more attributes than people, that's what we needed before, and B, some condition on the error tolerance, which is sort of, it's the square root of D divided by N. The exact formula doesn't matter. The point is that how much error this can tolerate will scale up relatively quickly with the dimension. So the more complicated the thing you're releasing, the more error that the method will tolerate. Up to some limit. There's really a maximum of this and 1 here, but we'll forget that. Okay. So what this tells us is that, again, in order to kind of that this problem of understanding what's leaked about individuals gets harder the more and more things you're saying, the more detailed and complex a picture you're trying to paint of the statistical properties of the data set. And this is a really simple example where all you're telling me are column-wise averages, but if you start talking about correlations or any other further, more complex summaries of the data set, then even more things are possible. Okay, and one note is that this works no matter how the distortion is performed. All right. So let me give you another example of this kind of thing. Let's look at machine learning as a service. So this is machine learning as a service is a thing these days. So there are companies like Amazon and Google that provide this. There's some training API via which data are submitted, data are submitted. And on the cloud, a model is somehow fit to these data. And now the idea is that that model is made available via a separate interface to other people who might want to pay to use it. Okay. Forget, API here is just application programming interface. It doesn't really matter. It's just, it's an interface. Okay. So the prediction API gets used as follows. People submit, let's say images, and those images are classified, or they see some information about those images, like maybe labels on whether or not they're pictures of, dogs or cats or sick people or whatever. Okay, so the data sets that are used for training these models are often fairly sensitive. They could involve various kinds of, financial transactions, user preferences, behavior, whatever that is. And the question is, how much does the prediction API tell me about the data set that was used to train the model? And in this paper that I mentioned earlier, what the researchers did was to say, look at this idea of Homer and say, well, maybe we can do the same thing. What if we imagine we've got some idea, we know there are some examples we know were in the training set, and so we'll feed those into the prediction API and see what kind of classification we get out. And then there are some examples that were some examples not in the data set, which are submitted, and you see what kind of classification results you get for those. And these classification results, in this particular example, they're numerical, so they give you sort of scores for each class. So imagine, I'm 95% confident it's a picture of a dog, 5% confident it's a picture of a palm on a beach or whatever it is. Okay, and so what they showed is that you could recognize the difference between the kinds of classifications you get on things that are in the training set, out of the training set, Indeed, the way you do this is, of course, by training a model to do this. So you sort of use the same exact type of technology that's going on under the hood here to train a model that can distinguish, a statistical model that can distinguish these types of classifications with some reasonable certainty. And they also showed, I mean, this was a lot of the technical work of that paper was going into showing that you could do this without even knowing much about what the thing in the cloud was supposed to be doing. Okay, that you could come up with one kind of class of attacks that works without for most of the models that they considered, all of the models they considered. All right, so what I'd like to sort of draw, the example, what I want to draw from these various examples I went through is the lesson that on one hand, we don't really know what aggregate means. Okay, so these are all things that seem to be very highly aggregated types of statistics, yet taken sort of when they're sufficiently complex, they do allow us to figure out things about individuals. And so we want sort of a way to think about this problem that gives us some assurance that we're kind of on the right track. So I'll talk about this idea that I mentioned that came up earlier, differential privacy, and sort of what it gives us in this context. Okay, so it's differential privacy is it's a restriction on the kinds of algorithms one can run on a data set. There are several deployed systems that are sort of use that as the guiding principle for their analysis. There are systems implemented by Google and Apple that track information about how people use their devices in a way that, fairly sensitive information, in a way that way Google and Apple have an assurance that what they're storing is not specific to any given user. The US Census Bureau is retooling the 2020 decennial census, the publication mechanism that goes with that, to, be based on this principle. And there are ongoing things at various other companies like LinkedIn and Uber and Facebook also on trying to make data sets that they collect somehow available to researchers in a way that they're sure that they've got a kind of an ironclad guarantee that they're not exposing individual users' information. Okay. It's also led to intellectual advances and a really, I think, fascinating field of research that's connected to questions in sort of algorithm development, cryptography and security, statistics and machine learning. Those are maybe not so surprising, but also some interesting connections to game theory and economics, programming languages, and recently law and policy. And I'll talk a little bit about that if I don't run out of time. All right, so let's try and just nail down what this definition is. So we've got an algorithm. So it's a restriction on the kinds of processes I can use to analyze a data set. So imagine I've got a data set. It's got n records. I'll just call them x1 through xn. I've got an algorithm that takes this data set and processes it and spits out an answer. The domain, like what kind of data we're dealing with doesn't matter here. It could be anything. The domain of the data doesn't matter. It could be, like each of these xi's could be just a number, but it could also be like your tax record. What we will kind of, we'll sort of restrict things a little bit. We're going to consider not sort of arbitrary algorithms, and I'll say what I mean by that in a second. We're not going to have a probability model for the data set. We're going to think of the data set for now as sort of a fixed thing, or we're going to allow it to be anything. But we will ask that the process that's analyzing the data be somehow probabilistic or randomized. And so what that means is that even if the data set is just one, even if there's just one fixed data set, every time I run the algorithm, I'll get a different result. And so this quantity, a of x, is really a random variable that could kind of range over some space. It has a probability distribution. And the randomness that goes into this procedure doesn't come from the data itself. It's sort of a separate source of randomness. And it could be involved by adding noise to the data. It could come from maybe resampling subsets of the data. There are lots of different things one can do. Sorry. Okay, and so our definition is going to be based on a thought experiment. And in the thought experiment, we're going to change one person's data, or maybe add them or remove them from the data set. And we'll ask, how does the probability distribution on outcomes change when we make this change to the data? Okay. So imagine I've got like one probability distribution when I've got on data set X. Now I'm going to consider this sort of hypothetical data set where X2 has been changed to some other value, some other tax record. Like my tax record has been replaced by, Donald Trump's or whatever. And now what we'll look at how these two distributions differ. And specifically, we'll ask that for any set of outcomes, any possible sort of set of outputs of the algorithm, and in particular, that means anything that could, any specific set of outcomes that could result from the publication of the algorithm, of the output, the probabilities of these things, of this set of outcomes, of the outcome lying in this set, is about the same, whether or not the real data are used or this sort of hypothetical data set is used. Okay? So for example, if I'm concerned about the event that I get denied health insurance, what I'm assured is that the probability of that happening is about the same regardless of whether or not my data are in the data set. Okay? Or rather, regardless of whether or not my data were used. Okay, so a little more formally, we'll say that two data sets are neighbors if they differ in exactly one person's data. And we'll require that neighboring data sets induce close or nearby distributions on outputs. And there's sort of a specific formalism that goes with that. We'll ask that for all possible subsets of outputs, or more generally events in an output space, if you're a mathematician, then the probability of the algorithm's output lying in that set is about the same up to some multiplicative factor, which we'll hopefully control, as it would be in the thought experiment. Okay? And so this definition is indexed by a parameter. It's this number. In this case, it's called epsilon. It's some measure of how much is being kind of leaked by the output of the algorithm. And actually, normally we don't use 1 plus epsilon. We use e to the epsilon for reasons that don't matter for the talk. Okay, so let's just play with an example to get a sense of what this definition looks like. So suppose I were to do a survey in this room, and I want to know the number of you who've cheated on a test, okay, ever. Let's say a test that mattered. Now, I could go to each of you and ask you, Adam, have you ever cheated on a test? Okay, I guarantee I can predict his answer. And I could ask an auditorium full of people, and they'd all give me the same answer. How do I get good statistics on something like this, where people are not necessarily inclined to answer honestly? Okay, so Warner was a statistician considering this type of question a long time ago. How do you get survey respondents to answer difficult questions? And so he considered this idea called randomized response. So simple model, let's say each person's data is just a bit, 0 or 1, yes or no, you've cheated on a test. Here's what I'm going to ask you to do. Each individual is going to just roll a die where I can't see it. Just roll a 6-sided die, a fair die. And if the answer is 1, 2, 3, or 4, they will report the true quantity. And if the answer is 5 or 6, they'll report the opposite of the true answer. Okay? And then the output of my process is just a list of reported values. Okay? So it looks kind of like this. I ask person 1 to produce y1, person 2 to produce y2, person 3 n to produce yn. And that's this whole process, that's my algorithm. And then the output is the list of outputs. Okay, so this is just in a nutshell what's going on. So why is this private, or why does it satisfy this definition we wrote down? Well, let's do the thought experiment. Let's change my bit. My bit's 0, of course. We're going to change it to 1. So notice that now the event that my report is a 1 it's more likely. So its probability goes up from 1/3 to 2/3. But it doesn't go up more than that. It can't go up by 1 million. Okay? And in fact, it's easy to argue that the probability of any subset of outcomes goes up by at most a factor of 2. Okay, so this would satisfy my definition with epsilon, which is the natural logarithm of 2. It's about 0.7. You could change this, you could, not with a fair die, but with like a little more work, not with one roll of a fair die, but with a little more work, you can get this ratio to be as close to 1 as you want it to be. And the question is, why is this algorithm actually useful for anything? And the answer is yes, perhaps a little surprisingly. It's not hard once I've got enough responses to get a very good estimate of the fraction of people whose true answer was 1, using the fraction of people who reported their answer to be 1. Okay, and if you're bored during the talk, you can think about exactly how you do that. And if you wanted to, if you sort of crank down this noise parameter epsilon, this leakage parameter epsilon, as it gets closer and closer to 0, then the kind of quality, the accuracy with which you can estimate this fraction goes down. I mean, that is, the error goes up. Okay, let me give you another example called the Laplace mechanism. So this, instead, I'm going to consider sort of a very different form of an algorithm. So in this algorithm, let's say we've got the same problem. I want to estimate the proportion of zeros and ones in the data set, maybe the proportion of people who cheated on the test, or the proportion of diabetics. So now the function I want to release is just the average of the x's, the proportion of them that are 1. And I'm going to consider a simple strategy where I first go and compute the correct answer using the data, and then add noise to it. Okay. And the question is, how much noise do I need to add? Well, to satisfy my definition. So there's actually a fairly clean answer to that, at least sort of at some level of generality. Given a function f, we'll first compute this quantity, which I'll call the global sensitivity. It's a maximum. It's sort of the most that this function can change if I go from the real world to the thought experiment world, where I've changed one person's data point. Okay? And I'm going to, if the function is just a single number, as in my example, then I'm just looking at the absolute value of the difference in the value of the function. If the function is a vector of statistics, then I have to measure distance of vectors in the right way. That's what these double bars are for. Okay. But like, for example, the proportion of diabetics, the maximum change you can ever get is 1 over n. If I change one person, the proportion changes by at most 1 over n. And so this global sensitivity is some measure of how much application of the function f sort of spreads apart neighboring data sets in this sense. What you can prove is that if the standard deviation of this noise is at least this global sensitivity over epsilon, then the algorithm satisfies our definition, at least if I use the right kind of noise. And the one right kind of noise is what's called the Laplace distribution. So it's sort of like this noise distribution you'd be sampling from has, its density has this form. So it's kind of like a normal distribution, but pointy. And this is like the form for the density, and this is scaled according to this quantity, the global sensitivity divided by epsilon. What you can argue is that if you add noise in this way, then it will satisfy the definition. And so if you're interested in releasing statistics for which this global sensitivity quantity is small, this is actually a pretty good way to do it. And there's various respects in which it's the best way to do it according to this definition. But just what's going on sort of intuitively, why is this a reasonable thing? Well, if I go to the thought experiment where I change one value, I'm basically comparing two different probability distributions which have been shifted relative to one another. And the amount by which they've been shifted is at most this global sensitivity. And so if I know something about these these probability densities, then I can figure out how much the probability of any event gets increased. Okay? And you can sort of do various things. If you want to release lots of proportions, you can do something a little more sophisticated than that. You can get noise, something like square root of d over epsilon per entry, with variant on the definition, which I'm not going to explain. But just to kind of give you a sense of where that relates to the things I was talking about earlier, those robust membership attacks that I was talking about a few slides back, they worked as long as the error that was introduced by the algorithm was less than this square root of d over n quantity. And now this algorithm, this noise addition algorithm that I told you about, works roughly as long as the noise we're introducing is above that magnitude. Okay, so this is, the mathematicians in the audience don't look too hard because I'm sort of hiding various things, and I'm happy to give a more formal statement of this result offline. But sort of morally, what's going on is that we've got this regime above. There's some sort of threshold where above this threshold we can analyze what's going on and we can get meaningful guarantees. And below that threshold, we actually have sort of implementable attacks that we can actually use. Okay, so there are lots of techniques people have developed for developing algorithms that satisfy this constraint. And there's noise addition. There's some sort of more general kind of exponential sampling type technique that actually turns out to be useful. And these two techniques taken together cover the vast majority of the algorithms that are known in the literature. Most of them are constructed by sort of combining these techniques in various clever ways. And then there's sort of another class of algorithms to which that randomized response example belongs, where we ask what they are called local algorithms because the data are perturbed separately by each person before being assembled all in one place. And those algorithms have various benefits in terms of whom you trust to manage the raw data. Okay, because the algorithms that work like this, you can in principle ask users to randomize their data themselves, to do that die roll themselves. And so you can avoid the need for a sort of a trusted central place where all the data gets piled. And you can use cryptography to get some of that in other models also. Okay, so this is just a sense of the kinds of things people do. Let me talk a little bit about what the definition means. So I wrote down a mathematical definition. I tried to give you some intuition for what it means, for what it is. This doesn't tell us it's a good definition or a useful definition. It's certainly not the only definition one could write down. So why is it that I think it's a good definition? Okay. So at this point, we're kind of leaving the math behind for a moment and asking, like, how do we, in general, how do you make sure that some mathematical concept you've constructed adequately captured some real-world notion you're trying to model? Right? There's no recipe for that. It's going to be context-specific. Generally, what we do is we sort of argue various things that are true about everything that satisfies this definition and use those to get a sense of whether or not we feel that these are like sufficient. So let me give you one thing that you can prove that I think is meaningful. But for that, I first have to set up a straw man. So this is a straw man on the slide. So here's what you might hope to be able to prove. You might hope to be able to prove something like, if you're running, if what you are seeing is the output of a differentially private algorithm and my data are in the data set, then one might hope that your beliefs about me will be the same after you see the output of the algorithm as they were before. That is, we might hope to argue that if what you're doing is differentially private, then people on the outside really learn nothing about any individual in the data set. And it turns out that's impossible to achieve. Okay? It's too strong. And I'll explain by an example. Suppose you know that I smoke. Okay? But, it's the 1960s. It's the first episode of Mad Men. There's no connection between smoking and cancer. Smoking is something that virile, healthy, good-looking people do. Now there's this clinical study that comes out that shows that smoking and various forms of lung cancer are strongly correlated. Okay? So that's a drag. But it's a drag for many reasons. One of them is that you've learned something about me. Okay? You knew that I smoked. Now you know that I'm a horrible health insurance risk. Now, so you've definitely learned something about me. But what that thing you learned about me was not because my data were in the study or not in the study. The study, maybe was done in Houston, where I don't live, right? What you learned about me was that the reason you learned something about me was you learned this fact about human biology, which is the whole point of aggregate statistics about clinical studies, right? So what differential privacy guarantees is not the thing up there, that's too strong, but it does guarantee the following: no matter what you know ahead of time, you learn almost the same things about me, whether or not my data were used. Okay, so the things you learned about me are essentially independent of whether or not my data were included. And this is, you can sort of formalize this in various ways. The one I find most convincing is using kind of a Bayesian framework where you imagine the attacker has some probability distribution a priori, and you look at how that evolves once they see the output of the algorithm. Okay. But in particular, the things that satisfy this definition, they provably resist the kinds of attacks I was mentioning earlier in the talk, at least when this epsilon parameter is not too big. Okay, so there's lots of now research, as I mentioned, on privacy. Some of it looks at definitional questions, some of it on things around similar to differential privacy, not all of them. Looks at developing algorithms that that satisfy the definition and do various useful things. Develop usable systems for working with data, according to this framework. As I mentioned earlier, there's work on sort of attacks and trying to understand what the limitations of these systems really are. And this sort of mirrors the role of cryptanalysis, for example, in cryptography, where you try to break cryptosystems to figure out how well you're doing. There are various work. There's a strong connection to cryptography, where you, in settings where you want to leave data distributed among various people and not collect all the data in one place. Often there are cryptographic protocols that help with that. And there are some interesting connections to other areas of science and academic study, like adaptive data analysis, which I probably won't have time to talk about, and some questions of law and policy, which I hope I will get to in a second. Okay, so just last thing, a couple of quick vignettes from ongoing research that's going on. This is not going to be about my research. I'll talk about that tomorrow. I'll talk about stuff other people are doing that I think is cool. Okay, so one is on fitting complex models subject to this constraint of differential privacy. So for a while, there was a sense that this definition of differential privacy was very strong, and maybe too strong to do really useful, complicated things with. And that understanding has changed a lot in the last few years, and people have looked at fitting what are called deep neural networks. So these are sort of a family of statistical models that can be visualized something like this. And that have been, these types of networks have been really key to most of the advances in artificial intelligence in the last few years, especially in computer vision and in speech processing. Okay. So what this sort of work does is to develop algorithms whose output is a deep neural network that fits the data reasonably well, and yet provably reveals sort of nothing about, or not nothing, but gives you the guarantee I mentioned earlier, which is it reveals approximately the same thing about me, whether or not my data are in the data set. Okay, so now we're taking, whereas the previous methodology for fitting these networks ended up producing networks that reveal a lot about their training data, we can now kind of get to the point where the training data are hidden. It also provides another advantage, which is that the model itself can be made public, because now I've sort of got this guarantee, so now I can publish much more than just the predictions I was making based on the models. I can publish the whole model. And if you want to play around with this on your own, there's it's been incorporated into TensorFlow, which is a sort of one of the leading kind of software frameworks for doing deep learning. So you can download the code online and play with it. Another sort of very different place where research is going is to look at interactions with legal frameworks. Okay? And in these interactions, there are really two central challenges that are quite different that are being addressed. So one is, given a body of law and regulation, like let's say there are laws regulating how sensitive information should be managed, I can ask, what kinds of technical definitions can I write down that actually comply with these laws? Like, what does it mean at a technical level to actually comply with the law? Okay. And this is challenging because generally laws, and for reasonably good reasons, laws are written not with very specific technical definitions baked into them, but with standards that are more of the form, a reasonable person with this type of skill should not be able to do X, right? So there's a lot to do to convert that into something actionable that we actually, can work with. And like an example would be the GDPR, which came out in Europe in last year, and which sort of has transformed, has given us like lots of consent boxes to click on different websites, but has transformed the way that European law talks about personal information. And then a sort of parallel but distinct line of work is on how should we write laws and regulations so that they make sense given evolving technology, right? So this is a very different type of question where you're asking, like, how do we write laws that won't age, won't be like technologically irrelevant before the ink has dried, right? And just as an example, a lot of the metaphors that are used in the law, for example, around surveillance, just don't make sense anymore. They talk about physical they talk about they're called wiretapping laws because you should have the image of someone with crocodile clips and a telephone wire. Okay, but those metaphors go out of date. And so how do we write policy? How do we formulate regulations in a way that actually sort of makes sense technologically? And this is an ongoing area, but the thing I want to impress upon you is that technical research has a big role to play in this, right? Because we need it to inform these conversations. Like, for example, this notion of personally identifiable information that plays a key role in a lot of existing privacy law, basically is not a meaningful concept in most contexts. And my colleague, Kobi Nassim, has been working on this a lot recently and has a couple of nice papers on how mathematical formulations relate to a couple of different legal frameworks. And so one on sort of a formal interpretation of FERPA, which is the law regulating your educational records. And then this concept of singling out, which appears in the GDPR a lot, but isn't given a technical meaning in the GDPR. Okay. So I wanted to talk last about some connections between privacy and what's called adaptive data analysis. So this is just a problem which a priori isn't at all about privacy, which is if I've got a data set that I'm reusing many times in a statistical analysis, how do I make sure that the analyses I'm doing remain statistically valid? And the issue that comes up is that when the questions I ask over the course of my analysis, the questions that I ask later in the analysis depend somehow on the outcomes that I saw earlier in the analysis. Okay, so this is a very common setup. But it's actually not the setup that's covered by classical statistical theory. Most of the things you'll learn in your statistics classes for forming confidence intervals and doing computing p-values for hypothesis tests and things like this, they rely on the assumption that first you pick the analysis, then you looked at the data. Okay? And if you don't do it in that order, then you break a basic independent assumption, and those p-values and confidence intervals and whatnot don't actually make sense statistically anymore. And the question is, how do you set things up so that you can get valid inference in these settings. Okay? And it turns out there's this lovely connection to privacy that was developed by, over the course of many papers, but it started with this paper of Cynthia Dwork and Vitaly Feldman, Tony Patasi, Omer Reingold, Aaron Roth, and Moritz Hart. And what they observed is that conditions like differential privacy help prevent overfitting or help introduce a certain form of independence in this setting that allows you to reason meaningfully about the statistical properties of your analysis, even when you're in this sort of adaptive setting where you're asking questions that depend on earlier answers. Okay? And privacy is not the only condition. Differential privacy is not the only condition that makes sense here. There are a few others, but they all have this sort of a similar type of flavor of relating to stability of the algorithm. Okay, so I'll wrap up. I'm a little over time, I'm sorry. I'll wrap up quickly. So I started the talk by reminding you that data are increasingly being used to automate decisions. And so these sort of data-driven systems are playing roles in more and more parts of our lives. And they have not generally been developed with sort of a security mindset going in. Okay? And that's partly because traditional computer security, if you take a textbook that says computer security on the cover, it's generally about sort of controlling intrusion in a system. There's like an inside and there's an outside, and you're trying to keep the people on the outside from the inside, and that's it. But in some sense, what we're coming to understand is sort of modern security really has to include a much broader collection of questions. Broadly, how trustworthy are these systems end-to-end, taken as a whole? So that implicates questions of privacy. It implicates questions of resistance to manipulation, fairness, accountability. And differential privacy gives us one formalization of one piece of that sort of broad collection of problems. Okay. I think it's an interesting piece. I think it's a useful piece, an important one. But it's really only a small part of this big puzzle. And I think that the question I'd like to leave you with is, what other areas need that kind of scrutiny and that kind of precision? And where can we be a lot more rigorous in the way we think about these questions? Thank you very much.